Every vector search needs an index, and the index you choose affects your memory footprint, query speed, and recall. Now, the most accurate option is a flat index, comparing your query against every vector in the dataset, which gives you 100% recall, but at the cost of latency. Now, if you're searching legal documents for liability clauses, you probably need that. But if you don't need that level of accuracy, that's where approximate nearest neighbor or AND indexes come in, trading an acceptable drop in recall for much lower latency. You'll likely be choosing between HNSW and IVF. And by the end of this video, you'll understand how they work and how they compare, so you know which one to use based on your latency targets and infrastructure constraints. And if you're just learning about vector search, you'll want to check out our What is a Vector Database video and the other episodes in this series to quickly get you across the basics. Let's get into it, starting with an overview of AND indexes and recall. Think of an AND index like finding a book in a large bookstore. You're not going to scan every shelf. You just head straight to the sections most likely to have what you're looking for. Now, you might miss some relevant books in other sections, but you'll find a good selection much faster. AND indexes make the same trade-off. They give up an acceptable amount of accuracy in exchange for a big gain in speed. The term used for that accuracy is recall. It measures how many of the expected results were actually returned. But recall isn't something your vector database can give you automatically, as it has no way of knowing what the correct results should be for a given query. That's why you need ground truth, a test set of queries where the correct results to return are already known. So for each query, we're essentially asking, how many of the correct results did we get back? If we were looking for the top 10 and we get all 10, that's perfect recall. If we get 9 out of 10, that's 90%. Now we do that across hundreds of queries, average the results, and that's your recall score. That's why evals are so important, because when you make a change, whether it's switching index types, changing an embedding model, or updating your data, evals give you quantitative evidence of how a change affects the quality of your results. Now let's dive into AND index details, starting with HNSW. To make these concepts more concrete, I've built a simple AND index playground that shows how results change as we adjust parameters. I'm using Facebook's AI similarity search library here, but pgvector and Actian Vector AI DB are also supported. HNSW, short for Hierarchical Navigable Small World, provides high recall at low latency and is a strong default choice. It's a multi-layer graph where vectors are nodes connected to nearby neighbors. The top layer is sparse, so searches start with large jumps across the space. Each layer down becomes denser with shorter connections for gradual refinement. And by the time search reaches the bottom layer, which contains every vector, it only needs to compare a small number of candidates to find the nearest neighbors. Here we're querying 1 million vectors. And quick disclaimer, don't read into the specific numbers too much. They're just illustrative of how recall and latency change as we tune parameters. The first thing to notice is the HNSW index at 747 megabytes is significantly larger than the flat index at 488. That's the cost of storing the graph connections on top of the raw vectors. Build time is also much longer than IVF. Now let's run a search with the default settings. We get 88.1% recall, and speed is an order of magnitude faster than the flat index. And that's the core AND trade-off right there. Now let's adjust EF search, which is a query time parameter that controls how many candidates HNSW considers before returning results. I'll bump it from 20 to 36, and recall jumps to 94.6%, but at the cost of more latency. But higher recall doesn't always translate to better outcomes. So the idea is to increase recall to the point it stops improving your results and is only costing you latency. So HNSW delivers strong recall at low latency, but there are 3 trade-offs worth knowing. First is the memory footprint. As we just saw, HNSW stores graph connections on top of the raw vectors, so the index is meaningfully larger than IVF. Now, how much that matters though depends on the vector count, dimensions, and available memory. Second is index maintenance. Inserts are handled incrementally, but updates and deletes will eventually require a rebuild of the graph, which is compute intensive relative to IVF. High churn is manageable if rebuilds can happen in off-peak periods, but if changes need to be reflected quickly, rebuild time may become a bottleneck as vector count increases. And third, the index is memory bound. HNSW relies on fast, random access across the graph, which means the entire index needs to fit in memory. Otherwise, performance degrades quickly if disk reads are required. HNSW is the default in many cloud-managed vector databases, and for good reason. Strong recall out of the box, and the managed infrastructure handles the memory overhead for you. The trade-off is usage-based pricing, which can become prohibitively expensive at scale. On-prem or at the edge, you don't have that elasticity, so memory and maintenance overhead can become real constraints. Now let's look at IVF to see how it compares. IVF, or inverted file index, takes a fundamentally different approach to how it indexes and searches vectors. Instead of a graph structure, IVF partitions vectors into clusters. Each cluster has a centroid, a synthetic point at the center of that group, calculated as the average of its vectors, and every vector is assigned to the cluster with the nearest centroid. IVF search happens in two stages. First, the query is compared against the centroids, which is cheap because there are far fewer clusters than vectors. That identifies the most relevant clusters to search, and then IVF searches within a subset of those clusters controlled by the nprobe parameter. Lower values search fewer clusters for faster results, while high values search more clusters to improve recall at the cost of increased latency. Looking at the playground results, IVF has comparable recall to HNSW at the default settings, but significantly higher latency with nprobe set at 12. Let's drop that down to 6. And now we can see that latency is edging closer to HNSW, but recall has dropped to 77%. This is exactly where HNSW has an advantage. It can reach higher recall at lower latency, but you need to be able to afford the memory and index maintenance overheads. But when you can't, IVF gives you a way to balance accuracy, latency, and compute at scale. So IVF has 3 structural advantages over HNSW. First is memory efficiency. No graph structure means the index is meaningfully smaller than HNSW, it's just vectors and cluster assignments. That also makes it much faster to build. Second is recall versus latency control. nprobe can be aggressively tuned at query time to adjust recall to meet use case specific latency targets. And third, scalability beyond memory. Unlike HNSW, IVF's cluster structure remains performant with disk-based storage, allowing indexes to scale to billions of vectors and beyond. The trade-off is recall tuning. To match HNSW's recall, IVF has to search more clusters, which pushes latency up. And because IVF tuning changes can shift recall quite dramatically, more careful tuning is required to dial it in. IVF isn't usually the default choice. It's the index you reach for when memory or scale become limiting factors. And that's especially true when it comes to on-prem and vector search efficiency. When you're running vector search on-prem or at the edge, you don't have elastic compute, so efficiency becomes critical. Query latency, memory usage, build time, and per query compute all directly affect the query volume your infrastructure can support. As scale increases, small differences in any of those add up quickly, especially in retrieval pipelines with hybrid search and re-ranking. That's why efficiency matters, especially in on-prem and edge deployments. Even with the same index and configuration, different vector search systems behave differently in terms of recall, latency, and resource usage. Industry benchmarks can give you a starting point for comparison, but the only way to know how a vector search system will perform for your workloads is to evaluate it against your own data and query patterns. You've now got an understanding of how HNSW and IVF are structured, how they search, and crucially, how to choose between them based on your latency targets, memory constraints, and update patterns. If you want to go deeper on the topics in this video, or just share what you're building, join the Actian community on Discord, The link is in the description. Thanks for watching, and I hope to see you in the next video.